Hi, this lecture is about quantum dots. Earlier, I mentioned quantum dot to you as an example of nanotechnology. Quantum dots are very well known when talking about nanotechnology, and that's because of their fascinating application and color change performance, which makes them very cool and interesting. But let's get more precise and see how they are working. Quantum dots are nanoscale nanoparticles, or in other words, they are nanocrystals of semiconducting materials. They usually have diameters in the range of 2 to 10 nanometers, around like 10 to 50 atoms. They were first discovered in 1980, and they display unique electronic properties intermediate between those of the bulk semiconductors and discrete molecules. And once again, I need to mention you, it's because of the unusually high surface to volume ratio of these particles and also quantum confinement due to limited number of atoms and the special shape of quantum dots. The most apparent result of this is the fluorescence, which is quantum dots can produce distinctive colors determined by their size and shape. But how is it working actually? Well, I need to tell you a little bit about the energy level first. If you remember, we said one of the quantum effects at the nanovolt is quantization, and because of that, whole energies are not allowed, right? That's true for individual atoms, and I mentioned that orbital shapes around also atoms relate to allowed energies, right? But in solid, when we have billions of atoms, these orbitals make connection, the concept of bonding actually. And by that, instead of single level of energy, we get a allowed region of energies called band of energy. In metals, these bands are continuous, but in insulators, there is a remarkable gap between energy bands. Semiconductors stay in between, have some band and not as large as insulators, but there is a still band. Like as this figure shows, in bulk semiconductor structures, two important bands are valence bands and conduction band. Valence band is the highest energy level band that electrons have occupied it. And conduction band is the lowest energy band that is empty. And there is a gap between these two, and this is so-called band gap. Band gap is a very critical parameter in many electronic and optical applications actually. And there are tons of research to tune band gap value. For example, if light is emitted to a semiconductor, some electrons acquire enough energy to jump from valence band to conduction band. And since higher energy level is not favorable, after a while, they may want to come back to the valence band and release the difference energy between the valence and conduction band. Yes, they release photons with the amount of energy equal to the band gap. And why does this matter for us? Because in quantum mechanics, energy relates to the wavelengths. As a matter of the fact, different colors that we see, there are different packets of photons with different wavelengths, or let's say energy reflected from surface of materials. Pretty cool. But what happens with quantum dots? Quantum dots have different size, shape, and made of limited number of atoms, right? So instead of energy band, we have some sets of energy, individual energy levels, but these sets of energy are very close together. But still we have the band gap between the sets of energies. Interestingly, depending on the size, or let's say the number of atoms, band gap change. And that's a good example of quantum confinement effect due to the size at the nanoscale. And you have realized different size of quantum dots have different band gap size. Once light hit them and afterwards electrons come back from higher energy sets to lower energy sets, they release different amount of energy, implying different wavelengths and different color. The smaller quantum dots size get, the larger the band gap, the more energy released, higher frequency, and we get more bluish color. Vice versa, we get more reddish color. Alright, sweet. Quantum dots, or nanoparticles of semiconductors, were theorized in 1970s and initially created in the early 1980s, and thereby they're artificial semiconductor nanoparticles. Quantum dots are artificial nanostructures that can possess many varied properties depending on their material and shape actually. The properties of quantum dots are not only determined by the size but also by the shape, composition, and structure. For instance, is it solid or hollow? The unique size and composition tunable electronic properties of these nanostructures make them very appealing for a variety of applications, and new technologies such as electronics like single electron transistor, optical applications like TV displays, solar cell, information storage, imaging, medicine, and even sensing. Let me show you some of the examples of quantum dots. Quantum dots, TVs, and display. The most commonly known use of quantum dots nowadays may be TV screens. Samsung and LG launched their quantum dot LED TVs in 2015, and few other companies followed not long after. Quantum dots, because of their unique physical properties, will be at the core of next generation displays. Compared to the organic luminescent materials used in organic light emitting diodes or LEDs, quantum-based material have pure color, longer lifetime, lower manufacturing costs, and lower power consumption. Another key advantage is that because quantum dots can be deposited on virtually any substrate, you can expect printable, flexible, and even rollable quantum dot displays of all sizes. Pretty cool. Another example of quantum dots is a biological and chemical application. Quantum dots are also finding important medical application, including potential cancer treatment. Quantum dots can be designed in such a way that they can be accumulated in particular parts of the body, and they deliver anti-cancer drugs bound to them. Their big advantage is that they can be targeted at single organs such as the liver much more precisely than conventional drugs, so reducing the unpleasant side effects that is a characteristic of untargeted traditional chemotherapy. Quantum dots are also being used in place of organic dyes in biological research. For example, they can be used like nanoscopic light bulbs to light up and color specific cells that need to be studied under a microscope. They are also being tested as a sensor for chemical and biological warfare agents. Unlike organic dyes, which operate over a limited range of color and degrade relatively quickly, quantum dyes are very bright and can be made to produce any color of visible light. Perfect, that's the end of the quantum dot lesson. See you in the next one. Take care.